In this lesson, we're going to be revisiting some of the problems we looked at early on, but this time we're going to be able to solve these problems using our limits, what we've learned about limits. Let's do a little review. How do we find the slope of a secant line? I'm going to draw a tangent line in here first. A tangent line touches the graph only at one point, whereas a secant line intersects the graph at two different points. How do we find the slope of that secant line? Let's label some points. First point we have is a f of a. Second point would be x f of x. This distance would be x minus a. That's our change in our x value. And this distance here would be the change in the y value from point P to point Q. So that would be f of x minus f of a. To calculate the slope of that secant line, we would take f of x minus f of a, all divided by x minus a. And that's the slope of our secant line through PQ. Mathematically, how can we represent the slope of the secant is approaching the slope of the tangent? We went through this process early on in this section. Let's revisit that process. We looked at creating a secant line through x equals a and x. So we looked at the slope of that secant line, and we said we could use the estimate for that slope of the secant line to estimate the slope of the tangent line. But we said that's not a really good estimate. So we moved the point a little bit closer to A, and then we created the slope of that secant line. And we said, well, that's even a better estimate for the slope of the tangent line. And we saw we could repeat this process. We could find a point even closer to A. And notice, we are using points that are on the graph of this function. So we could find an x value and the corresponding y value. We created the secant line through those 2 points, and then we calculated the slope of that secant line. And we repeated the process. And every time we let x get closer to a, we saw the slope of the secant line was getting closer to the slope of the tangent line. This is how we found the slope of the tangent line. Notice the f of x minus f of a divided by x minus a represents the slope of the secant line. But when we take the limit of f of x minus f of a divided by x minus a as x approaches a, then we find the slope of the tangent line. Notice that this right here is the slope of the secant line, but we also call this the difference quotient. When we take the limit of the difference quotient as x approaches a, we are finding the slope of the tangent line at a. Now, our study of limits, we have been looking at the limit of some function as x approaches a, for instance, and we're just getting a value, say L. We were just finding the value that this function was approaching, the y values, as x approached a. But now we're transitioning to finding the limit of the difference quotient, which is actually going to find the slope of the tangent line. An example, find an equation of the tangent line to the function y equals x squared at the point 1, 1. If we take the limit of f of x minus f of a divided by x minus a as x approaches a, we will find the slope of the tangent line. Now, a in this case is 1. So we have f of x minus f of 1 divided by x minus 1 as x approaches 1. Notice that is where we're trying to find the slope of the tangent line, at 1. Now if we plug in f of x, we see f of x is our function. That's where we're getting x squared. Then we have minus f of 1. Well, if we plug 1 into the function, we would get 1 divided by our x minus 1 as x approaches 1. If we tried direct substitution on this limit here, we would get 0 over 0. We get the indeterminate form. But we know how to deal with that now. We know we can factor this one. We can reduce the x minus 1s. And now we can use direct substitution. And we get 2. This is the slope of the tangent line to the curve of y equals x squared when x equals 1. The slope of that tangent line is 2. To find the equation of the tangent line, we know the slope of the tangent line would be 2. We know a point on that line would be at P, 1, 1. So we could replace x and y with 1, 1, solve for b, and we have the equation of our tangent line. Let's look back at the original problem we discussed a few moments ago. We are going to make a substitution for x minus a. We're going to let x minus a equal h. When we make that substitution, we could solve for x by adding a to both sides, so x would equal a plus h. So over here, we're going to substitute a plus h for that x, and then x minus a can be replaced by h. How would that change our points? The notation for those points. Okay, if we make those substitutions, let's now rewrite our difference quotient. And you see I've inserted the new points into our graph, and we would get f of a plus h minus f of a. That's just our y sub 2 minus y sub 1 all over a plus h minus a. That's our x sub 2 minus x sub 1. Now in the denominator, the a's do cancel. This is the same as what we were looking at earlier. This finds the slope of the tangent line at a. Notice, however, that this says h is going to 0. Well, that has the same effect as x approaching a in our other form, because h is the distance from here to here. Well, if h is going to 0, that means we are taking values closer and closer. This means h is getting closer to 0. And so you'd see the slope of your secant line is getting closer to the slope of the tangent line. Now this was as opposed to our other form. These two find the same thing. They both find the slope of the tangent line at A. You're going to see probably 95% of the time we're going to use this form instead of this form. We do use this form here sometimes when we're trying to show that a function may be differentiable at a point or not. That's typically when we use that. There are a couple other instances where we use it. But like I said, most of the time we'll be using this form, and we need to memorize that form. An example, find an equation of the tangent line to the hyperbola f of x equals 3 divided by x at the point 3, 1. In order to find the equation of a tangent line, we need the slope of the tangent line. So how would we find the slope of that tangent line? We're going to use our limits. Notice we're using the form, the limit of f of a plus h minus f of a all divided by h as h goes to 0. That's what we're using, this form. Now we know in this case a equals 3. That's where we're trying to find the slope of the tangent line. So plugging in 3 for a, we get this. And then plugging 3 plus h into our function, we get this limit. Now, if we use direct substitution back where I have circled that limit, if we use direct substitution, we would get 0 over 0, the indeterminate form. So we're going to get common denominators and simplify. So in the next step, we got common denominators in the numerator, and the 3's cancel. So then we would get the limit of negative h divided by h times 3 plus h as h goes to 0. If we tried direct substitution, we'd still get 0 over 0, but we see we can reduce the h's. So if we reduce the h's, and now we can use direct substitution, and we have found the slope of the tangent line at a equals 3. The slope of the tangent line is negative 1/3. Now we could find the equation of that tangent line by using the point 3, 1. And this time I use the point slope form of the line. So that is the equation of the tangent line. And if we wrote it in general form, we would get x plus 3y minus 6 equals 0. That's still the equation of the tangent line at a equals 3. Now on the computer, I graphed 3 divided by x. You can see the purple graph. Then I graphed the equation of that tangent line we found. And you can see the line is tangent to the graph of 3 divided by x at x equals 3. And I wrote the equation of the line also in slope-intercept form. Find the slopes of the tangent lines to the graph at the general point, a square root of a. So we're trying to find the slope of any tangent line to the graph of the square root of x. And you see this problem says at the general point a square root of a. We're not specifying a point. So we should get some expression at the end of this process where we can plug in any value that we want to find the slope of the tangent line. The process is exactly the same. We're using the form f of a plus h minus f of a divided by h and taking the limit as h goes to 0. Plug in a plus h to your function to get the square root of a plus h. F of a is square root of a. If we use direct substitution at this point, you would see we get 0 over 0. We know at this point we got the indeterminate form, so we need to manipulate that expression so we can use direct substitution. So hopefully you're thinking multiply by the conjugate. When we multiply that all out, remember the first two multiplied together in the numerator would give us a plus h. The two middle terms cancel each other. Then we'd have negative square root of a times square root of a gives us negative a. The a's cancel in the numerator. Now we can reduce the h's. And now we can use direct substitution. And notice we have 1 divided by 2 times the square root of a. We can now find the slope of the tangent line wherever we would like to for this function. So that's the difference between the last problem and this problem. The last problem, we specified we wanted to find the slope of the tangent line at a particular point of x. So when we got our final answer, we had the slope of the tangent line only at that point, at x equals 3. But for this one, if we leave this as a, we then come up with an expression at the very end where we can now plug any value of x we want in and find the slope of the tangent line at that point. So you can see if you're trying to find the slope of the tangent line at multiple points, you would want to find the slope of the tangent line at a general point A, and then you can just plug in whatever you want after you found your expression. If we chose some values for the square root of x to find the slope of the tangent line, say at 1, 1, a would equal 1. So we would just plug in 1 for a. We'd have 1 divided by 2 times the square root of 1, which is 1/2. If we wanted to find the slope of the tangent line at x equals 4, we would just plug in 4 to the expression we found, and we would get a slope of 1/4. The square root of x looks something like this. So at x equals 1, we would say the slope of this tangent line is 1/2. And out here at 4, if we looked at the slope of that tangent line, we would see the slope of this tangent line is 1/4. At the point 9, 3, we would have a slope of 1/6. Now let's take a look at velocities. Let S equal f of t represent the position function of an object where S is the displacement of the object from the origin at time t. In the time interval t equals a to t equals a plus h, the change in position, we would plug those values into the function to find the change in your position. So we'd have f of a plus h minus f of a. That's our change in position. We know to find the average velocity, we take displacement divided by time, and we just said f of a plus h minus f of a represents our change in position, or the displacement, and the time would be our a plus h minus a, which reduces down to h. So this would calculate our average velocity. Now here's just a way of looking at this on a number line. Say here's our position at time A. This right here would be representing f of a, our starting position. Here's our position at a plus h, sometime beyond a. So if a was 2 seconds, if t equals 2, well, a plus h would be sometime beyond 2, so maybe 5 seconds or 10 seconds, whatever the time interval was. Now this is representing the distance that we've traveled at f of a plus h. So the distance between those 2 points would be found by f of a plus h minus f of a. If we had a position function that looked like this, here we have, using the second form of the difference quotient, calculating the slope of that secant line, we'd have f of a plus h minus f of a divided by h. And that's the exact same thing we find on the prior slide. This was our average velocity. If average velocity is f of a plus h minus f of a divided by h, how would we find instantaneous velocity? Hopefully you thought, well, if I take the limit of the average velocity as h goes to 0, that will find our instantaneous velocity. This means the velocity at time t equals a is equal to the slope of the tangent line at point P. An example, suppose that a ball is dropped from the top of the CN towers 450 meters above ground. What is the velocity of the ball after 5 seconds, and how fast was the ball traveling when it hit the ground? Now, we looked at this problem earlier on when we were estimating the slope of the tangent lines by using our secant lines. But now we should be able to refine this process using our limits. Now remember, Galileo's found that an object's motion, a free-falling object, can be modeled by f of t equals 4.9 t squared. That's how far the object has fallen after a seconds, or t seconds. To find the instantaneous velocity, we would use this formula. So for part A, if we're trying to find the velocity, remember after 5 seconds means at 5 seconds. A would equal 5. That's when we're trying to find the slope of the tangent line. However, we're going to leave in A as A. So at the very end, we're going to get an expression in terms of a, but we can just plug in any value that we would like to find the slope of the tangent line at that point. So our function that we're using is f of t equals 4.9 t squared. So you can see we plugged that in. We plugged our a plus h into that to get 4.9 times a plus h squared minus 4.9 a squared. That's our f of a, all divided by h. And if we use direct substitution at that point, you can see we would get 0 over 0, the indeterminate form. So it looks like if we expand this one, we can cancel some things, and we're left with the limit of 4.9 times 2ah plus h squared divided by h as h goes to 0. Now if we factored out an h, we could reduce the h in the denominator, and we can now use direct substitution, and we have 9.8 times a. Now if I wanted to find the slope of the tangent line when a equals 1, I would just plug in 1 for a. If I want to find the slope of the tangent line when a equals 3, I plug in 3 for a. We want to find the velocity of the ball at 5 seconds. So we would plug in 5 for a, and we'd get 49 meters per second. That's the velocity of the ball at 5 seconds. Now, part B asks us, when will the ball hit the ground? Well, if s of t is how far it's fallen in t seconds, we want to know when it's fallen 450 meters. So we would say s of t equals 450. Our position, we want it to have fallen 450 meters. So if we can solve this equation for t, we would be able to determine the time at which the ball hit the ground. So just divide both sides by 4.9, take the square root. We'd only take the positive value. We don't want the negative value because we can't have negative time. So it would take 9.6 seconds for the ball to hit the ground. Other rates of changes. Suppose y is a quantity that depends on another quantity x. Thus y is a function of x, and we write y equals f of x. If x changes from x sub 1 to x sub 2, then the change in x is, remember delta x means the change in x, we just take x sub 2 minus x sub 1. Now the corresponding changes in y, we would just plug those values into the function and subtract them. And remember, delta y means the change in y. The average rate of change, we would use the difference quotient. Now since we're not working with a position function, this does not necessarily have to represent an average velocity. It's now just an average rate of change. So if we're talking about sales for a company, it'd be the average rate of change of sales. It does not have to be average velocity. A graphical representation looks very similar to what we've done in the past. So this would be our change in x. This would be our change in y. It looks that the change in y bracket is a little bit lower than it should be. Instantaneous rate of change. We know that if we take delta y over delta x, which is the difference quotient, and we take the limit as delta x goes to 0, we get our instantaneous rate of change. An example, temperature readings in Celsius were recorded every hour starting at midnight on a day in April in Whitefish, Montana. The time x is measured in hours from midnight. The data are given in the table. So we are given a table of values. Find the average rate of change of temperature with respect to time. The first part from noon to 3 p.m. Now, this says that the temperatures were recorded every hour starting at midnight. So this must be midnight. So this must be noon, 12 hours later. So if we want to find the average rate of change of temperature with respect to time from noon to 3, well, if this is 12, 1, 2, 3. Average rate of change, we're going to use the difference quotient. So we'd have 18.2 minus 14.3 divided by 15 minus 12. Let me see if I can do the math here. This appears to be 3.9 divided by 3. And that appears to be 1.3. And that's degrees Celsius per hour. Then it says from noon to 2. So again, we're going to use the difference quotient, 17.3 minus 14.3, all divided by 14 minus 12. So we would get 3 all divided by 2, which is 1.5 degrees Celsius per hour. And from noon to 1, we would have 16 minus 14.3 divided by 13 minus 12. That looks like 1.7 divided by 1. Then part B asks us to find the estimate of the instantaneous rate of change at noon. Looking at the slope of these secant lines, it looks like it may be approaching 1.8, 1.9 or something around there. But let's take the secant line from 11 to 12 and then 12 to 1 o'clock and then average those two. This is a technique we've used before. So we would have 16 minus 14.3 divided by 1, which is 1.7. That's the slope of the secant line between 12 o'clock and 1 o'clock. Now between 11 and 12, we have 14.3 minus 12.1 divided by 1. That looks like it's 2.2. And now we're going to add those together and divide by 2. So 1.7 plus 2.2 divided by 2 looks like that would be 19.5. So our estimate for the instantaneous rate of change at noon, if that is all correct, let me see, if we take, oops, I'm sorry, I put the decimal place in the wrong spot, 1.95. We have 1.7 to 2.2 would be 3.9 divided by 2, which is 1.9. Okay, so it looks like it is 1.95. So that's our estimate for the instantaneous rate of change at noon. Why does something feel wrong here?